Have you ever wondered what powers the sun, the star that gives life to our planet? The answer lies in the heart of the sun, where a process known as nuclear fusion takes place. Imagine the sun as a colossal engine fueled by hydrogen atoms. These atoms, under extreme heat and pressure, collide and combine to form a heavier helium nucleus. This process is known as nuclear fusion. The transformation from hydrogen to helium releases a tremendous amount of energy, the same energy that lights up our sky and supports life on Earth. But don't confuse nuclear fusion with nuclear fission. While fusion combines lighter nuclei to form a heavier one, fission splits a heavy nucleus into two lighter ones, a process currently used in our nuclear power plants. Each process has its own unique benefits and challenges, but both harness the immense power stored within the nucleus of an atom. Now that you understand the basics of nuclear fusion, let's dive deeper into the science behind it. In the heart of the sun, nuclear fusion is happening every second. But what exactly is going on? Well, let's break it down. Picture, if you will, the sun's core. It's a seething mass of energy with temperatures reaching a staggering 15 million degrees Celsius and pressures that are over 300 billion times greater than what we experience on Earth's surface. It's these extreme conditions that make nuclear fusion possible. Now, fusion, as the name suggests, is all about coming together. It's the process where two light atomic nuclei combine to form a heavier nucleus. In the sun, this happens when two hydrogen atoms collide and merge, forming a helium atom. But this helium atom weighs slightly less than the two hydrogen atoms that created it. It's not a case of bad math, rather it's Einstein's theory of relativity in action. You see, the missing mass from the hydrogen atoms isn't lost. It's converted into energy following Einstein's famous equation E equals mc squared. Here, E is energy, m is mass, and c is the speed of light. So even a tiny amount of mass can create a huge amount of energy. This energy is what powers the sun and produces the sunlight that reaches Earth. But if fusion is so efficient, why don't we use it for power on Earth? Well, the challenge lies in creating the right conditions. We need to achieve temperatures and pressures comparable to those in the sun's core. And we need to do it in a controlled way that's safe and sustainable. In the sun, gravity does the hard work, maintaining the pressure and temperature needed for fusion. Here on Earth, we don't have that luxury. So, scientists are exploring other ways to achieve these conditions, using technologies like magnetic confinement and laser heating. So, the energy we see as sunlight is actually the result of countless fusion reactions. Imagine if we could harness that power here on Earth. The quest to unlock the secrets of fusion and bring the power of the sun to Earth is one of the greatest challenges of our time. But imagine the possibilities if we can make it work. Harnessing the power of fusion on Earth is no easy task. But imagine the possibilities if we could. Fusion power is the process that lights up the stars, including our own sun. It's the merging of light atomic nuclei to form heavier ones, releasing vast amounts of energy in the process. This energy, if harnessed, could provide us with a virtually unlimited supply of power. But how does this translate to our world, our Earth? Well, think clean, abundant energy. Unlike its cousin nuclear fission, which splits heavy atoms to release energy, fusion doesn't produce high-level radioactive waste. This means we could be looking at a future with an energy source that doesn't contribute to the environmental crisis, a very real concern in our rapidly warming world. Moreover, fusion doesn't come with the risk of a meltdown, a safety hazard that has long been associated with nuclear power. The ingredients for fusion are plentiful, found in seawater and lithium, eliminating the need for risky mining operations and geopolitical conflicts over resources. But as with any great scientific endeavor, there are challenges to overcome. The conditions required for fusion to occur are extreme. We're talking about temperatures hotter than the core of the sun and pressures that dwarf the deepest ocean trenches. Yet, despite these hurdles, progress has been made. Researchers around the globe are developing ways to confine and control these extreme conditions. There's the tokamak, a donut-shaped device that uses magnetic fields to contain the hot plasma. And there's the stellarator, a twisted version of the tokamak, designed to maintain a continuous fusion reaction. Other methods, like inertial confinement, use lasers to heat and compress the fuel, triggering a fusion reaction. These are just a few examples of the ingenuity and innovation at play in the quest for fusion power. While we are not there yet, the potential of fusion power is truly exciting. The journey to harness the power of the stars is filled with challenges, but the promise it holds for a cleaner, safer and more abundant energy future is truly worth the pursuit. So, what does the future hold for nuclear fusion? As we peer into the horizon of possibilities, one thing is clear. The race to harness the power of fusion is well and truly on. Around the globe, teams of scientists and engineers are working tirelessly, pushing the boundaries of our understanding and technology in pursuit of this game-changing energy source. One of the most significant initiatives in this field is the International Thermonuclear Experimental Reactor, or ITER project. A collaborative effort involving 35 nations, ITER aims to prove the feasibility of fusion power on a commercial scale. The project is currently constructing a tokamak, a device designed to confine and control the plasma needed for fusion reactions. It's a colossal endeavor, a testament to human ingenuity and determination. But the journey to fusion power is not without its obstacles. The challenges are monumental, from engineering hurdles to the sheer cost of research and development. Yet every challenge presents an opportunity for innovation. And with each step forward, we inch closer to a reality where fusion power is not only possible but practical. Imagine the implications. Fusion power offers the promise of virtually limitless clean energy. It has the potential to revolutionize our energy landscape, reducing our reliance on fossil fuels and curbing the effects of climate change. The stakes are high and the rewards even higher. But perhaps the most exciting aspect of fusion power is its potential to inspire. As we strive to unlock the secrets of the stars, we are reminded of our capacity for exploration, for innovation, for progress. It's a thrilling testament to the power of the human spirit, to our relentless pursuit of knowledge and advancement. Nuclear fusion might seem like science fiction today, but with ongoing research and development, it could become science fact. And when that happens, we might just have a small star right here on Earth, powering our lives.